let's talk about some of the polar curves you're going to encounter in calculus. So we're going to talk about the Rose curve first. This is the general formula for the Rose curve. A times sine or cosine of n theta. So we're going to talk here about some of the what some of these components mean and what they can signify when you're graphing it. So if you want, you might want to take these notes down while looking at some graphs or take a picture or whatever, pause it. But let's go over some of these. What does the A mean? So the A is the length of the petals. So Rose curve has petals, it looks like a rose, pretty basic. But the A value is the length of the petal. So if A was 4, the length of each petal would be 4. If A was 3, it would be 3. You can get it from there. So what does sine and cosine mean? If it's sine, that means the Rose curve will be symmetric over the y-axis. And if it's cosine, then that means the Rose curve will be symmetric over the x-axis. And then what does the n mean inside the brackets? So if n is an odd number, for example 1, 3, 5, whatever, the Rose curve will have an n number of petals. So if it's 3, the Rose curve will have 3 petals. If it's 5, the Rose curve will have 5 petals. But if n is an even number, like 2, 4, 6, then the Rose curve will have 2 n petals. So if, like for example, n equals 2, then the Rose curve will have 4 petals. If n equals 4, then the Rose curve will have 8 petals, and so on. Okay, here are 2 examples of the Rose curve. So here we have 4 sine 3 theta, and over there 2 cosine 2 theta. So just like with any other graph, when you're going to start graphing them, you have to plug in points and go from there. And there's no way around it. But what we can do from looking at this graph and the equation is maybe we can predict some of the qualities of the graph based on the equation. So if you look at the petals for this one, you'll notice that the length of the petals, 1, 2, 3, 4, is 4. And the A value for the equation is 4. So those match up. The other thing is sine, right? There's sine in this graph. So because it's sine, you see this Rose curve is symmetric to the y-axis, as you can see. And the third thing is, since it's 3 pi, or 3 theta, the n value is 3, right? So that means we have 3 petals, which is what we see here. And then in the second graph, the A value is 2, which means the length of our rose petals should be 2. 1, 2. The function is cosine, so this Rose curve is actually symmetrical to the x-axis, and we can see that. And the third thing, the n value of the Rose curve is 2. So when the n value is even, that means we have 2 n petals, which explains why we have 4 petals here. Okay, now let's talk about the limit zone polar curves. So the equation for the limit zone polar curves is r equals a plus or minus b sine or cosine n theta. So in this case, the n doesn't really matter. So let's look at the other aspects or components of this equation that we can maybe predict in our limit zone polar curves. For one, sine and cosine make a difference. So if there's a sine function in your limit zone equation, that means your limit zone curve will be symmetrical to the y-axis. If it's cosine, then the curve will be symmetrical to the x-axis. Another thing to note is that if it's a plus b, so like right here it's plus or minus, if it's a plus b, then you will find that your curve is going to be on the positive side of the axis. So for sine, since sine goes up and down, it'll be on the top half, and for like cosine, since it's left and right, a positive axis would mean it would be on the right side. And you can tell, same thing for the negative axis. If it's a minus b, and then the rest of this, it'd be on the negative part of the axis. So we'll see when we do the examples what I mean by that. The second thing we have to look at is the A value and the B values of the equation. So if the A value is less than the B value, then your limit zone curve will be a looped limit zone. If the A value is greater than the B value, then the limit zone curve will be a dimpled limit zone. And that's how you figure out what type of limit zone it is. Secondly, you have to know what the A value and the B value is. A plus B, the A value plus the B value will be the length of the limit zone from the origin to the end. And we'll see this in the graphs. And the last thing, for looped limit zones, the length of the loop is the difference between A and B values. And for dimpled limit zones, the length of the dimple is the difference between the A value and the B value. So now let's look at some graphs. Okay, let's just look at some examples of polar curves. So as you can see in these examples I've chosen, 2 of them have sine as the actual function, 2 of them have cosine as the actual function, 2 of them have a plus in the middle, and 2 of them have the minus in the middle. As well as 2 of them have a greater A value, these 2 have greater A values, and these 2 have greater B values. So all these differences add up, and we can see them, we'll see it in these 4 graphs. So for the first one, 2 plus 5 sine theta. So here's a graph of 2 plus 5 sine theta. And as you can see, the length of the loop is 3. And we know that the length of the loop is 3 because the difference between B and A is 3, which indicates that the loop is 3. Second thing, the length of the whole thing, the length of the big thing from the top to the origin is 7. And we know this because A plus B, 2 plus 5 is 7. So that's how we got that. Notice how this curve goes up. And because it's on the sine, it's a sine function, it should be symmetrical to the y-axis, and it goes up. And we know this because it's a plus here, there's a plus in the middle, which means it's on the positive part of the axis. And as you know, you should have already told by now, because A is less than B, this is a loop limit zone. And this is another example of the loop limit zone. It's looped because, again, A is less than B. But this time there's a minus in the middle instead of a plus, which means it's going to be going on the negative part. So this, because there's a cosine here, this loop limit zone is symmetric across the x-axis. And because it's negative, it's going to be on the negative part of the x-axis, which means it's going this way. And then the length is 7, as we can tell, 2 plus 5 is 7, A plus B, and then the length of the loop is 3, because the difference between B and A, 5 and 2, is 3. And that's how we got that graph. Now let's look at these dimpled limit zones. So for the dimpled one, A is 5 and B is 2. And the plus, there's a plus sign here, and there's a cosine function. So because it's a cosine function, we know that it's going to be symmetric across the x-axis, and we can see that here. And because there's a plus in the middle, it's going to be on the positive part of the x-axis, which is why most of it is going to the right. And then if we look at the A and B values for the length of the limit zone, 5 plus 2 is 7, right? So that's why we have from the origin to the end of the limit zone, the dimpled limit zone, that's 7. And then for the dimpled part, this back part, is the dimpled part. We know that the length of the dimple is going to be the difference between A and B, which in this case is 5 and 2 would be 3. The difference between 5 and 2 is 3, which is why the length of the dimple is 3. And then for the last one, a last dimpled limit zone, the difference is that there's a sine function and that there's a minus in the middle. So because it's a sine function, this limit zone is symmetrical across the y-axis. And we can see that here. And because there's a minus in the middle, it's going to be on the negative side of the y-axis, which is why most of it goes down here. So again, the length of the limit zone from the origin to the end is going to be A plus B, 5 plus 2, 7, which is why this whole thing is 7, as you can see here. And the length of the dimple, this back part, is going to be the difference between 5 and 2. The difference between A and B, sorry, which is the difference between 5 and 2, which is 3. And this is why you see it here. So these are some examples with a lot of variations. And hopefully with these components and with these predictions that you can get from the graph and the equation, you can figure out how your graph would look.
Okay. Now we're going to continue our series on polar graphs, and we're going to cover the circle and the lemniscate. So starting with the circle has a formula of r equals a sine theta. This orange part can also be cosine, or there doesn't have to be anything there, which would mean it would just be r equals a. So a couple things about the circle formula. A is the distance from the origin to the edge, also known as the radius. And if you have sine here, it is symmetrical to the y-axis. Cosine is symmetrical to the x-axis. And if there's nothing there, so if it's just r equals a, then your circle is centered at the origin. The next thing is a lemniscate. This looks like an infinity sign. There should be an equal sign here. R squared equals a squared sine or cosine to theta. So to cover what these are, A is the length from the origin to the end of the loop. So it's the length of one infinity part of the symbol. And then if you have sine, your graph is diagonal, so it does not touch any of the axes. If it is cosine, it is across the x-axis, so the graph is symmetrical over the x-axis.
And r equals 4. So let's look at some of these components. So for r sine of theta, we notice that it's going up on the y-axis. Basically, it's symmetric to the y-axis, and we can predict that because the sine function is in this polar curve. So we knew this was going to happen. Other thing we knew was going to happen is that the length from the edge of the curve to the origin is 4. And although it's easier to notice it this way, you can also notice it sideways because it's a circle, right? It has to go 4 on each side. From here to here is also 4. So that's the polar curve r equals 4 sine of theta. R equals 4 cosine of theta is similar, except that it's going along the x-axis because because it has the cosine thing, it's symmetric to the x-axis. So as you notice, because there's a 4 right here, the a value is 4. The length from the origin to the end is 4. And then if we go here, the last circle, the different type of circle, it's r equals 4. There's no sine, there's no cosine. So what that means, it's going to be centered on the origin, right? Like we talked about. And the 4 here signifies the length from the origin to the edge, which we can see here. Here's some examples of lemniscate polar curves. So we have two today. R equals the square root of 9 cosine 2 theta, and r equals the square root of 16 cosine 2 theta. So why does it look different from the formula that we talked about before with the r squared? Well, precisely because of that. We usually write lemniscates as r squared equals a squared times cosine or sine, then 2 of theta. But in the calculator, if you're plugging these graphs into a calculator, you can't plug in r squared. So naturally, we just take the square root of both sides, so we can just get r and then plug in this part. So it's really simple to tell what we did here. So we took the square root, and then 9. What does that mean? 9 is, in this place, is a squared, right? So in this case, because there's 9 here, that means the a value of this equation is 3. And we can see that because the a value signifies the length from the origin to the end of the curve, and that length is 3, as you can see here. So the a value equals 3 because this is 3 squared. What does the cosine do? Well, the cosine means it's going to go across the x-axis. So that's what we see here. It's going across the x-axis. And yeah. So in this second curve here, we have the square root of 16 sine 2 theta. So as we noticed before, the 16 here isn't a, it's a squared, right? So if 16 equals a squared, then a equals 4. And we can see that because the length from the origin to the end of the curve is 4. And the graph would, the equation will tell you that. And because it's sine, because sine is the function, the lemniscate is going to go diagonal. So you can see that it goes kind of diagonal this way. And that's how the graph would look.